the next episode of John Conway's Spirit Seminar series. Today we have a very special speaker who is also a visiting foreign faculty here with the IMM program, Professor Marco Abate. Most of you are already familiar with him. So he is from University of Rome, and particularly his area of interest is complex geometry. But today he's going to, I think it will be an epiphanic lecture where he will be reliving about the lost root, something you might have came across, but the underlying fact was unnoticed, and it will be a surprising, fun-filled, and some mystical kind of mathematical mysteries that he is going to unfold today. So over to you, Professor Marco Abate. Thank you very much for coming to LAMS and accepting our invitation.
Thank you everybody for being here, and I would like to heartily thank the organizer and everybody here at LAMS for the invitation and the wonderful hospitality, which unfortunately is too short, but that's my fault, it's not your fault. Okay, what I'm going to talk to this morning is a story which is somehow connected to my research work, not directly, but it's close enough. And we are going to start with a very basic question that has been addressed even in high school. And we'll start from the 17th century. And as you see, there will be, we'll do a time travel through a few centuries up to the beginning of this century, when this problem has been solved using very deep, I should say, contemporary mathematical techniques, completely different from what was expected at the beginning. So, what's the problem? Roots. We would like to solve the equation. We would like to find the roots of the polynomial. Okay, this is a typical problem. But what does it mean to find the root? We are used to have the formula for solving the quadratic equation when the degree is 2. And this was already known by the Babylonians 1,000 years ago. Then in the 16th centuries, the Italian mathematician found formulas for solving the cubic equation, degree 3, and the fourth degree equations. These are formulas given in terms of the coefficient of a polynomial. Okay, what happens to hybrid degrees? Well, a surprising and very deep result by Galois at the beginning of the 19th century was that such formulas for degrees higher than 4, from degree 5 and on, they do not exist. So it is not that we didn't find it, they cannot exist. Because this has something to do with the structure of the group acting on the root, on the permutation of the roots, and when the group becomes too complicated, then it is not possible to write such a formula. Anyway, formulas are theoretically nice. It's a good thing to have them. But they're not necessarily the best mean to actually compute the roots. Even computing a square root, we cannot get a precise result. We have an algorithm, actually. Our computer or our phones have an algorithm. They taught me when I was in high school, but in the middle school, they taught me the algorithm for computing a square root. But I think that to my sons, they didn't teach it. So but the computer knows it is an algorithm, it is a procedure that starting from the equation produce you approximations of the roots as good as you want. I mean, the roots will be usually real numbers, so we infinitely many decimal digits. And so the best we can do, we are finite being, the best we can do is to get a finite approximation, possibly as close to the actual root as possible. This means that if you would like to solve this equation, maybe adding a formula is not the only way to go. The important thing is to have an algorithm helping you to get as close as you can to the roots. As close as you want, actually, not as you can. And this has been already thought about in the 17th century. First by Raphson and Wallace, which were two mathematicians which are, well, not well known. And then Newton started working on it. Well, all of us know who Newton was. And so their idea was exactly to, instead of giving a formula, to provide an algorithm so that you can start with a guess of a root, x naught. Then you apply this procedure, this algorithm, and you get a new number, x1, which is closer to being a root than the starting one. And then you repeat the procedure. You take x1, you get x2, which is even closer, and then x3, which is even closer, and so on, with the idea to approximate the actual root with an arbitrarily good precision, as close as you need in that particular situation. Okay, so that's the idea. What is the algorithm? And it was proposed by Newton. And the idea is the following. You start with a polynomial. Actually, you can do also the other functions, but let's say a polynomial. You pick a starting point, x naught. Then you draw the tangent line to the graph of a polynomial in that point. And then you take as x1 the intersection of this tangent line with the real axis, with the x-axis. In formula, let's see if this works. This one. Yeah. This is a formula. You take the x naught and then you subtract the value of a polynomial divided by the derivative. In particular, if x naught is a root, p of x naught is 0, and so you stay there. You do not change. Let me show you in a picture how this works. This is a polynomial. This is actually this polynomial over here. We start with some x naught. Then we go down up to the graph. Then we take the tangent line, and we follow the tangent line up to the axis. And we get x1. We repeat the procedure. We get x2. And if we repeat it once again, we get a very good approximation of a root in just 3 steps. Okay, but this is an example. Maybe an example that I chose so that it works to be, to give you a good impression. But we are mathematicians, so we have to actually prove that this method works. And indeed, Kelly, which is another English mathematician, and now we are in the 19th century, explicitly pose this question. But does Newton's method really work? Does it produce all the roots of a polynomial? Well, Newton was Newton, so he had an answer. And his answer was yes, if one starts from a value close enough to a root. Actually, Newton was able to prove it is not difficult, that if you start close enough, then you get closer and closer at a quadratic rate. So essentially, at each iteration, you gain, I think, 2 decimal places, decimal digits. So really, with just a few iterations, you get a very good approximation of the root. But, and this was Kelly's question, but if we do not know where the roots are, how can we be sure to start close enough to one of them? We do not know where they are. We just start with a random choice. Does it work or not? And well, he tried to answer this question starting from the easiest case. But to start with this case, which is the quadratic case. But to do this, he reformulated the problem in a different way to make things more understandable. And this reformulation, you'll see, it's a dynamical one. Okay, let's consider the rational function x minus px over p prime x. Rational because p is a polynomial, so p over p prime is a quotient of polynomials, so it's a rational function. Recall you that let me go back 1 second. Here, it should be here. Previous one. Yeah. This is a formula really. Okay, we're taking the function f, is just the right hand side of this equation. Back there. Let's see again this example, very fast. Here. Okay, so it takes this function. Then take a complex number x naught and put x1 is equal to f applied to x0. I will comment on the complex number instead of real number in a second. And then you repeat it. Okay? From x1, you get x2 applying again f. From s2, you get x3, and so on, you get xn. You are iterating the function f. You're building a discrete dynamical system generated by a function f. So, you get a sequence, given x naught, you get a sequence xn, which is called the orbit of x naught in this dynamical system. It's easy to show that if the sequence converges to some number xc, then necessarily f of xc is equal to xc. Xc is a fixed point for this function f. But the function as f is given by this formula. So if you get that f of x equal to x, like here, clearly x and x cancel, and you get that p of x should be 0. So a fixed point here is exactly the 0 over polynomials. And so what Kelly is saying is that, okay, I have this function, I iterated it, assume that this orbit converges to a point, then that point is a root of our polynomial. And so the question becomes, when this sequence does converge? For which starting point x0 the sequence does converge? Clearly, this is a statement that can be done on real numbers. We start with a real polynomial, we were looking for real roots. But you know well that when you're studying polynomials, it's better to go in the complex plane, even the coefficients are real, because in that case, you know exactly how many roots are there. There are d counted with the right multiplicity. And well, you have more space to go with. Instead of a line, you have a whole plane. And well, we'll get more beautiful pictures I will see in a second. It's easier to draw pictures in the plane than in the real life. And anyway, if you solve it on the complex plane, clearly you have a solution also in the real plane, in the sense that if this HC is real, then it is a solution of the real polynomial. Okay, so Kelly tried to answer this specific question, and he started with quadratic polynomials. It turns out that for quadratic polynomials, it's easy. I mean, it can be given as an exercise to master students. It turns out that if you start anywhere except, there is just one exception, anywhere on the line, then the Newton algorithm works in the sense that the sequence of you get applying the function f we saw before actually converges to a root. More precisely, the idea that the only point you have to exclude is the middle point of interval between the two roots. And by the way, the p is quadratic, so it's a parabola. The middle point between the roots is where the derivative is 0, so our function f is not even defined there because we have to divide by 0. But if you avoid that, if you start on the left, you are going to the left root. If you start on the right, you're going to the right root. And actually, you can do it even on the complex plane. And it turns out that instead of removing just the middle point of a segment, you have to remove the axis of the segment between the two roots. And if you start on one side of the axis, you go to one root. If you start on the other side of the axis, you go to another root. In particular, this is a good result because the measure of the axis is 0. If you take a random point in the plane, it will not be on the axis unless you are incredibly unlucky. And so it means that if you input the Newton method in a computer to solve quadratic polynomials, it works. And let me show you a picture of what's happening. And the polynomial is very easy polynomial, square minus 1. So the two roots are 1 and 2. 1 is over here and 2 is over there. And in green are the points which converge to the root 1. In blue, the points converge to -1. And you can more or less see, it's clear here, what happens starting from this point. At the first step you get here, second step you get here, third step you get here. At the fourth step, you are essentially right. Okay, same thing on this side. If you're interested to happen, what happens if you really want to start in the axis here, you just stay there. But I mean, he should be very, very unlucky or very masochistic to start with. Okay, so this is a quadratic case. What happens for a cubic case? Cayley tried and tried and tried, and he didn't get anything. He had no way to, he was not able to understand anything what happened there. And actually, the only thing that was clear that middle points, axes, Euclidean geometrical approaches, ideas to concepts seem to be completely useless. There was no way to use them to get any results. To the point that he was not even able to understand what kind of questions should he ask about the set of points where a Newton method actually was working. Yeah, they were open, but well, remember, this is the 19th century, they didn't know topology at the time. So even the work I just used saying that is an open set, it was not there. We didn't know what it meant. And I should say that Cayley has his reasons for not understanding what was going on. And now we know, because now we can make pictures, and a picture is not a proof, but gives you an idea how complicated the situation is. We saw what happened for s squared minus 1. Let's see what happens for s cubed minus 1. This is what happens. S cubed minus 1 has 3 complex roots. One is here, it's 1, and then you have 2 complex roots, one over there and one over there. Again, I colored it in red the starting points conversion to the root 1, and blue to starting point conversion there, and green the starting point conversion. As you can see, the situation is very complicated. And now we are going to zoom in this picture, I think around here, if I remember correctly. And so you see that it keeps being complicated until level. Let's start. No, come back here. Why it is not working? Yeah, maybe you have to wait a minute. This morning was working. Okay. Let's get here. Let me do it directly here. Maybe. Yes. Okay, you see, you get this structure over and over and over. You can keep going down and keep having this incredibly complicated structure. Yes, this boundary is a fractal. This is a typical example of fractal. And this is only the beginning. Now I'm going to show you another few pictures of what happens applying the Newton method for different polynomials. Okay, this is, you see 4 colors, so this is a 4th degree polynomial. And now I stop counting the colors, so this is higher degree polynomials. And as you can see, well, this is, I think, 11, 12 degrees polynomial. The situation is very complicated. But keep in mind one thing, notice that we have this channel going to infinity. Okay, this will be important at the end. In the center here, it is a mess. It's an incredible mess. But, and somewhere it keeps being a mess also going to infinity, but there are some parts which are apparently better behaved. And there is also other kinds This is an enlargement of the previous one. And this is an enlargement of enlargement of an enlargement. And again, this is just an excuse to show you some beautiful pictures. But you can understand why Kelly was not able to understand what was going on. Okay. The black, you see the black one. Okay, the black here. Let me show. Let me explain you how these pictures are drawn. The idea is the following. You start, of course, by computer. You start with a point, and you keep iterating it, and you stop when you are close enough, if the next iteration is very close to the previous one. The color, then you assign the color depending on where you are ending up. And the shade of the color you see also here is not just green, and has several shades of green. It depends on how many iterates you needed to stop, essentially. The black is because in, let's say, 1,000 iterates, the procedure didn't stop. Most of the time, and this is one of these cases, the reason it didn't stop is that the situation is so complicated over there that 1,000 iteration was not enough. You needed actually 10,000, 1 million iteration. So these holes here are just a computer problem. But we'll see other holes later on. Okay, these are very complicated things. Can we say about it something about it?
So it shows that the method is not converging in the case of complex numbers.
No, not yet. For the moment, well, maybe it wasn't a good idea. For the moment, these are just drawing. The problem is still open. Mm-hmm. I mean, it's still open in the talk. I give you an answer of it. What this thing shows is that to answer is difficult. In these pictures, which are, I mean, computer pictures, so they do not prove anything. In these pictures, the Newton method is working because everything is colored. Mm-hmm. So, except at the boundary between one color and the other, the procedure is working, it's producing a root. This is a question mark for this moment, because the black dots, the black areas, could be due to computer problems, and this is the case in this picture, or some other problem. So this is the reason we still have a question mark at this point. But to get there, we first need to understand at least something about these pictures. And this was something that Fatou, which is a French mathematician, and now we are in the 20th century, Fatou and Julia, but Fatou worked explicitly on this kind of Newton's method, try to understand. And his first question was, do this image has something in common? Is there some property, geometrical property, topological property, which characterize all these pictures? And Fatou was able to prove yes, there are many properties and now I'm going to describe one of them. Remember, this was in the 1920s, no computers, not pictures. Julien Fatou got an incredible amount of information on these sets without being able to draw them. It was really an amazing result. So let's ask a apparently completely unrelated question. How to cut the plane into pieces so that both pieces have the same boundary? Okay, you said this is very easy. Just take a circle. The interior and the exterior have exactly the same boundary. Or I can take two half plane, which is not, it is not a coincidence that it is the same picture we saw before. Again, they have the same boundary. Or you can take essentially anything. Whatever you draw in the plane, you divide, whatever, to be more precise. Whatever Jordan curve you draw in the plane, it divides the plane in two open sets with the same boundary. Actually, this is a very difficult theorem to prove. It's a typical example of a theorem that when you see it, you say, well, it should be obvious, and then you need 2 hours to describe the proof. But it is true. So the next question is how to put the plane in 3 pieces and all the same boundary. Well, you think a bit about it, and the answer apparently is it is impossible. As soon as you write a little piece, a little segment or little curve, it divides, you have only 2 sides of a curve. So can I get 3 sides? Okay, 1 point you can do it, but beside that point, how could you? Well, apparently it is impossible. Or is it? Well, what Fatou realized is that it is actually possible. The point is that the boundary is not made by lines, by curves. It is made by points in a very complicated manner, and the Newton method provides solutions to that. This is, for instance, what happens with this 4-degree 4 polynomial. Again, we have 4 roots considered by 4 colors. And if you see at each point in the boundary, you get all 4 colors get in there. At each point, which separates. Of course, the pieces are not anymore connected. You need infinitely many connected components to do that. But at each point, you get all 4 colors. And we can take some enlargement, and you can see it, it keeps being like that. Essentially, all points are like this. All of them. And of course, a picture is not a proof. What Fatou gave is a formal proof that this happens anytime you apply the Newton's method. And actually, almost any time you iterate a rational function. Okay, so we now know something about these sets. They're open, they typically have infinitely many connected components, they touch each other everywhere, but still we do not yet have an answer to carry this out. Okay, well, now we can draw them, but does Newton's method work? In the picture we saw the boundary, which is where Newton's method does not work, is very small. It has a zero measure, and so again, starting from a random point, you'll get a solution. The method will converge to a root. But those were just pictures. Maybe there are other situations. And indeed, this was at the end of the 70s, beginning of the 80s, I think. Somebody noticed this strange polynomial, adding these black holes there. So even if it is a cubic polynomial, instead of having just three colors, green, yellow, and red, we had a fourth color, black. That did exactly the same thing as before. That is, it turns out that each point in the boundary is touched by four colors. And after one realized that this is, we'll see in a minute, this is not a computer program. This is actually black color. Starting there, the sequence of iterates does not converge. And then it turns out that it was possible to do it with a much easier polynomial. For instance, this one, just taking s squared minus 2x plus 2. And this is the picture. And again, we get these black holes. And what's happening is that if you start iterating, we'll see in a second, starting from a black hole, sooner or later you end up going back and forth between two of them without converging anywhere. In dynamical system terms, there is a periodic orbit of period 2. Yeah. So you're not converging to a fixed point, but you're converging to a periodic orbit, to a attracting periodic orbit.
And how to compute, how to identify the black hole for this particular polynomial?
Well, because as soon as you understand that the problem is the existence of attracting periodic orbits, what you do is to iterate twice, so you get a polynomial degree 6, then compute the fixed point of this polynomial degree 6, and you check the derivatives of this at this fixed point. If the derivative is less than 1, then you get an attracting orbit. What happens, of course, you shouldn't do it for the polynomial, you should do it for the Newton method to settle the polynomial. Of course, some of the fixed point of the f square of the two iterates will be the fixed point of f, and so they will be the roots. The point is to check the other ones, and it is possible, for instance, in this case, to prove that you got the second iterate as a fixed point, which is not a fixed point of the first iterate, and where the derivative is less than 1, so it is attracted. And the basis of attraction is exactly given by these black holes. And indeed, let me show you what happens. In this case, we started from a little red. Actually, it was even longer than this. I think we started from here, down here, in this red region, and we then get there, then we get up there, then we get down here, and then finally the big red region, and then we started converging very fast. This is the same thing starting in a green region over here, small green region, so we need a number of steps to get in the big green region, and then the convergence starting to be very fast. Same thing for blue region. This time we started up there, and when we down, down, down on the left, and finally on the big blue region. And this is what happened starting from a black region. We started from that black region over there, then we went down there, then down to this one, down this one, and then we started going back and forth between this relatively large black region and this very small black region. And it is, you keep going back and forth. So, yeah.
So it's a kind of singularity in the complex plane of this complex function. Can we say that?
No, there's not really a singularity. I mean, the existence of periodic points is a standard thing.
Mm-hmm.
Most what you can prove, actually, what already Fatou and Julia proved, is that the large majority, of course, you have infinitely many periodic points to change the period. For each period, you have a finite number of them, but in total, very many. But what Fatou and Julia were able to prove, it's a beautiful proof, is that in the one which are attracting or indifferent, it is a derivative in modulus equal to 1, are only a finite number. The large majority of them are repelling, because derivative in modulus greater than 1. The repelling ones does not provide any problem, do not provide any problem for a Newton method, because nothing is convergent there. They are just pointing away. So you might have, at the very worst, a finite number of attracting periodic points which are not fixed points, which is okay. No, there are not many, but the black regions, as you saw, they have a positive area. So if you start with a random thing, a random point, you might be unlucky and start from a black area. And so in that case, the Newton method won't work. This was the situation in the 80s, and in the 80s, for this reason, the people trying to solve equation using the computer stop using the Newton method and start using other algorithms which are there. Because, well, there was a possibility to start from a point which was not given a root. But then, a number of people, in particular John Hubble, with his collaborator Dirk Schleicher and Scott Sutherland, came back to this problem because they studied in very much the behavior of dynamical systems on the complex plane. And as I show you, the reformulation by Kelly amounted to study a dynamical system, the iteration of a rational map on the plane. And they had this idea. Up to this point, I kept saying that the question was, if I start with a random point, does the Newton method work? The answer to this question, we saw it, is not necessary. But Hubble, Schleicher, and Sutherland asked me, why should I start with a random point? Why I cannot choose a good point to start? And this is exactly what we did in this paper appeared in 2003. Yes. On invenciones matemáticas, which, as you may know, is one of the best is not the best journal in the world for mathematics. Let's say one of the three best. And their answer is, okay, we can do it. We can find a set of good points so that starting from there, not from a random point, we are sure to get all the roots of the polynomial. And these points are explicit. They gave an explicit procedure to build this point. And this is just to write better the title of the paper, which is very clear, how to find all roots of complex polynomials by Newton-Smith. This is exactly what they do. And as you, oh, sorry. And, it's a 50 pages paper using very deep tools coming from complex dynamics, quasi-conformal geometry, complex analysis. And what they did is the following. Given a degree d, you just need a degree of the polynomial. They constructed a set SD contain approximately the number of points, 1.11 times d times log d to the square, so that for every polynomial p of degree d, the set SD just depends on the degree d, does not depend on the polynomial, and every root of the polynomial, there exists at least one point in this set, so that if you apply the Newton algorithm, this point will converge to that. So to find all the roots, you just need to operate with Newton methods on all the points of this set SD, which are not many. I will give you some numbers in a moment. And you follow those. Maybe some of them will not converge, but you're sure that following all of them, you'll get all the roots of a polynomial. And these are the numbers. So for qubit polynomials, you just need 4 points, essentially. For quartic polynomial, you need 9 points. Degree 5, you get 15 points. Degree 10, you get 59 points. And degree 50, you get 850 points, which from a computer point of view are not many. The growth of this number is just slightly above linear. It's d times some logarithm, which doesn't really matter. So it's almost negligible growth as from a computer point of view. How did they compute it, found these points? Well, this is a picture for a polynomial degree 50. In the previous pictures, I typically showed you this part of the picture, where all the masses, and so the picture are not beautiful. But what they proved, and it is difficult to prove because this proof should work for all polynomials, all Newton methods of all polynomials, is that what actually happened, and that these channels that I mentioned before, if you remember, I told you to remark there were channels going to infinity. They are always there. Okay, in this case, we have the most visible are yellow, but if you look inside, there are blue, red, and all 50 colors of them are there. Not only that, but, and this is the most difficult part of the proof because it is quantitative, they were able to estimate how large they are. what is the distance between one channel and the next, and the next. And so, how to find a good starting point? You need to find a starting point inside one of these channels. Now you know how large they are. If you put enough points close enough, closer than the smallest distance between two subchannels, you are sure that you are going to hit all possible channels. Here it's the drawing. Let's get an enlargement. So this is what they did. Okay, they put points in this way, very close to each other, but how close it depends exactly on this estimate about the width of these channels. And of course, here you have complicated stuff, a channel complicated stuff, but doesn't matter because you know that you are hitting all of them, keeping this point very close. Okay, so this from the algorithm for finding this point is very explicit. As soon as you have a degree, there is a recipe, clear recipe to make this point, showing how far away it should be and how close to each other it should be. But as I told you, this is from a theoretical point of view, is a beautiful result. Using deep argument of contemporary mathematics, it gives you a solution to a century-old problem. But as I was telling you, the other point is, okay, but now you want to have a practical algorithm giving you in reasonable time all the solution, and the numerical algorithm, mathematicians were using other algorithms. If it is okay, the Newton methods work, so we are very happy, but if it is too slow compared to other algorithms, we will keep using those other algorithms. Well, it turns out this is not the case, and this was done. Okay, this is what I already said, the kind of tools they had, and there's the other comment I'm making here is the tools they used, they were discovered and perfection at the end of the 20th century just for theoretical reasons, just because we wanted to study the dynamical system and a complex plane. But it turns out we have also practical application, because in 2012, Schleicher, one of the collaborators in this paper, was able to better further the procedure of choosing the points and then applying the Newton method, so that the algorithm he got was as fast as efficient as the other algorithm we were around. And this is still true. I mean, there's a colleague of mine in the Department of Mathematics of Pisa. He's a numerical mathematician, and did some study on this. And we talked about this, I think, a couple of years ago. And he said, which is still the case, the Schleicher version of this algorithm is still among the best and fastest algorithms that one can use to find the roots of polynomials. So we needed 4 centuries, but at the end, we were completely able to solve this problem and to find all the roots that Newton lost at the time. Thank you.